Okay. I don't know, like we're already like 4 minutes in, so I suggest we start. So, hello everyone. Today we are very much delighted to host Dr. Germano Sacco. And this is the first talk in our Synergy talks. And the main aim of this series is that we spark some conversations around the synergies between different working groups and how to interact with each other and also understand like what has been done in different working groups. So, I mean, we have like taken this initiative to invite Germano, but of course, like if you have other speakers that you think would fit into this concept, please do get in touch and invite your speakers as well. Like we're going to reach out to them, invite them, etc. So, Germano is currently leading the star formation and young stellar population sub working group within the WST Galactic working group. And he's very recently submitted a science case in the Galactic working group, of course. And so, a little bit of background on his studies. So, right now, he's a senior researcher at the Enough Archetri located in Firenze, in Italy. But he obtained his PhD at the University of Palermo, then moved to USA, and he was a postdoctoral research fellow at the Rochester Institute of Technology, and he got back to Firenze again. And until this day, like he has remained there, and it has been a pleasure to work with him on very different topics. He's very active in star formation and evolution from very different aspects. And he's an expert mainly in the spectroscopy of young stars, and he's been like involved with very different projects, like for example the European Galactic spectroscopic surveys like Gaia ESO, which some of us know as JAS, Foremost, and eventually Moons. So yeah, today he's going to talk about the star formation in space and time with WST, which is like a very specific topic related to WST in the Galactic Working Group. And yeah, the floor is yours, Germano. If I have forgotten anything, please do feel free to add to it.
No, thank you very much for the invitation. It's a really good idea. I think that we will have to collaborate and coordinate with the time domain working group. We already discussed that in our working group. We decided that for the moment, it's useful to have this some science case that overlap, so we can see from different point of view if you want. But of course, it's at some point we will have to converge to something to work together. So what I will present today is a bit the science behind the idea of carrying out a large survey of young star with the WST. This work it's still in a preliminary stage and has been done with colleagues that are joining the sub-working group on star formation. This is a sub-working group of the working group of galactic astronomy that I'm leading together with Carlo Manara, and this work is based on this first draft of template that we wrote together with the people listed in this slide that include Sara and Fateme that are actually following the talk. So, so we already have a general picture of how star form in our galaxy. We know that star form from the collapse and fragmentation of a molecular cloud that is structured in filaments that have been studied in detail using mainly infrared observation. These stars, then we can observe stellar system embedded in molecular cloud when we can study simultaneously star and gas, typically younger than a few million years, and then the stellar system, in most cases, dispersed in the galactic field, but in some cases, the estimate is about 10% of the case, they form star cluster. Despite we have this general view, we still have, there are still several issues that are open. the physical process leading the formation of a cluster, and especially the dispersion of star cluster are still debated, and we still, for example, don't know why some system form open clusters, some not, and what system form open cluster, one not. We know that the formation of stars and the property of star planet is influenced by the environment, and but still this is not clear. And what is more important, probably what will be the scope of studies if we look at 30 years again, we want to link the star formation study, the physics that we can study at local scale, to studies on large-scale structure, chemodynamics of the galaxy, and also beyond the galaxy. Star formation studies are very active also at the very local level, so at the level at the scale of the astronomical unit, when we look at the single star. Here, even we know since many years that the protostellar cores form a disk rotating around them. This disk accrete material onto the star, material that are ejected in bipolar outflow, and then the disk gradually dissipated and until they form a planetary system. However, there's still a lot of debate and discussion about the physical processes regulating this accretion process, what is driving the dispersion of the disk, and again, it is not clear if this process change when you change the environment in which the star form. Spectroscopy can have an important role in this study. Did have an important role in this study for many years. This is a beautiful spectra taken by work from my friend Carlo Manara, when you can show an X-shooter spectrum of a young star, and you can see that there are two components. The photospheric emission that you can see in all the star, and on top of that, the emission associated to the accretion phenomena in blue, and studying both components. These components are normally overimposed, so you have to separate, which is not easy, but you can do a lot of physics. You can study kinematics, radial velocity you can measure radial velocity from the photospheric spectra, and combining with Gaia data, you can study three-dimensional kinematics. You can study chemical abundances. You can measure ages of the star, and from the ages, then you can derive mass of the star. There are several spectroscopic indicators of ages, and you can, studying the emission component, measure, for example, mass accretion outflow rate, so to study the star-disk interaction. Finally, last but not least, overimposed to the spectrum of the star, you can see also the spectrum of the nebular emission of the gas that is around the star. So you can use a spectroscopy also to study the nebular emission associated to the gas that the parent gas where star formed. Coming back to the more general view, this field had a lot of evolved a lot during the last, let's say, 5 years, mostly thanks to the Gaia space mission and several surveys that were associated with them, like, for example, Gaia ISO, or even the Apogee survey. And I will show very few results, but I think what the main progress that we had in the field in the last 5-10 years. First of all, we discovered that young star formation are formed by several small subgroup in a sort of hierarchical structure, and this is seen both in space and velocity in the velocity domain, and we see that in several star-forming regions. We started combining Gaia and data from spectroscopy to study the kinematics of this star-forming region, and we see that all nearby star-forming regions where we were able to do that are expanding, and so they are probably dispersing in the field. More importantly, Gaia discovered a large amount of young stars dispersed across the whole galaxy. Before Gaia, we believe there could be this population, but was not really known. But still a lot of debate. What is the origin of this population? This population actually formed in low density structure, so you can have a star formation in high density cluster, as many people believe, but also a formation in low density structure, or these populations the results of the cluster that are dispersing in the field. And there are several, a lot of work actually has been done, a lot of paper that found this kind of results. Finally, this is very recently combining Gaia data and data of other surveys, the different group discovered the large structure across the galaxy. In particular, in the 2020, the group led by Joao Alves discovered this Galactic wave that is a 2 kiloparsec wave located nearby the sun that includes many of the star-forming regions nearby the sun. And this is actually, it look like the star formation, the local star formation is related to this large wave structure. And more recently, Eloisa Poggio, using a star younger than a giant younger than 100 million years, discovered even a bigger structure. This is far away respect to the sun. A 10 kiloparsec structure, even a wave-like structure. This is not related to the Radcliffe wave. These are really a new area, a new field that is opening thanks to mostly to Gaia, to the Gaia survey. So if you look at the local locally, instead, you see here there is a sketch of a young star. Young stars are extremely complex object. As you see, you have the star, then you have the disk. The disk is truncated by the stellar magnetic field, and the stellar magnetic field that channel the material that generate a shock to the star. And what we want to do is spectroscopy is measure mass accretion rate to understand what is regulate mass accretion rate. To do that, you can use either the continuum emission emitted by the accretion shock. Later, if you want, I can explain better the physics, or you can use the emission light that are found in the UV part of the spectrum. And a lot of work has been done by, in particular, Carlo Manara and many Italian folk, Juan Alcalá and X Shooter and instruments like that. And they studied several regions measuring, and they found that essentially there is a steep relation between mass accretion rate and mass. Mass accretion rate go with the square root of the mass, but also a very large scatter. Still, the origin of the scatter, this error is very complicated to calculate, but it seems that the scatter is real and not necessary to variability, and there are also hint of a bimodality. So it seems that but still have to more work has been done, that the slope of this trend change for low mass star. Something that is important to stress, and this is why I will tell you, because I will speak about WST, that all these regions are within, let's say, 200 parsecs from the sun, so very close by. Then this is an area where Fatema probably is more expert than me, and so she can answer the question. But we know since many years that the young stars are variable objects, and several studies been done, for example, by the group based in the US, in California, to study variability of in photometric domain, several even several survey with multi-band object, and also some theoretical work has been done for studying this kind of variability. And this is, for example, and MHD model of the young stellar system done by the group in Palermo. And you can see that you can clearly this system have a variability. This is the variability on shorter time scale. Not much has been done, or at least not at this level, and is done with spectroscopy. Then, as I say before, star formation can be affected from the environment. One of the effects is that if you have in young star forming a very massive star that emit a strong high energy radiation that go from the UV, but is also now we are discovering that in this young star formation there are also gamma ray emission, and this can induce photoevaporation of the protoplanetary disk. This can be seen by imaging in the proplyd. This has been discovered in Orion, but I observed, for example, these proplids in Sinus OB association. And you can see, for example, if you do more statistical study, this is the fraction of the star with disk as a function of the far ultraviolet flux that impact on the star, calculated considering the massive star in the region. And you see that the fraction clearly decrease with increasing the far ultraviolet flux. Another issue that is being discussed for many years, but still we don't have a conclusion, mostly for the lack of instrument, it's the relation between metallicity and the property of the disk. There are some results that based on photometry, that observation especially in the young cluster in the outer galaxy, which are more metal poor than the solar neighborhood, they show that the disk lifetime is much shorter. But on the same time, there are some results found by the group of De Marchi and collaborator, Guido De Marchi and collaborator, that found some young star with an age of 30 million years with still accreting. This is very unusual. Having said that, I have to say that these highly debated results, especially for the age, not much for the accretion. Now there are JWST observations that demonstrate that the star are actually accreting, but estimate of age are very complicated when you have an accreting star. So for all this reason, a lot of us will be busy in the next few years doing spectroscopy of young stars. And there are several the survey that are started or will start soon. The Sloan 5, we started the Abyss survey, that is quite rich survey of stars, young stars with both apogee and BOSS. Very soon, actually, hopefully in the next start of 2026, we will start our survey with Foremost. We are very excited. We will observe 100,000 stars in the solar neighborhood, and there is a companion survey more focused on young cluster. Sarah is also involved. And then WIV will have a program on young star. And finally, very soon, hopefully in 1 year, MOONS will online. It's an infrared spectrograph, and we have a program of young cluster with MOONS. However, so most of these instruments, except the moons, are on 4 meter or less telescope. So of course, the amount of flux we can collect is limited, and therefore most of these are limited to the still to the solar neighborhood. In our case, with foremost that we go up to M star, we arrive to 500 parsec. The Sloan arrive a bit larger, but it's a lower resolution. So it's anyway, it's all in the solar neighborhood. And its region in the solar neighborhood are all at solar metallicity, and also are biased because typically the density of this region is lower than typical density of star formation in the rest of the galaxy. And to my knowledge, there is nobody studying variability in this survey, at least for what I know. So what do we want to do with the WST? So we want to do a very large survey for mapping young star across all the Milky Way. So go beyond this limit. And this is, we want to do that making a follow-up of a young star detected with the LST. This plot is a simulation done by Loredana Prisinsano that studied studied the science case of young star in the context of LST, and they estimate that LST will detect a million of stars across the whole galaxy, and up to a magnitude, I think they arrived to 23, 24, and so the idea is to follow up this sample to go beyond this 2 kiloparsec, much beyond this 2 kiloparsec, and now we still have to understand exactly, because we don't have the ATC of WST yet, what part of this sample we will follow up. We can be able to follow up, but the idea is to starting from this LSC sample. And what are the goals? First of all, we want to study the structure, the dynamics, and the Milky Way using young star. Young star, as the work done, for example, by Eloisa Poggio demonstrate, are very powerful tool to study Milky Way because they are dynamically cold, and they are where they formed. So they are not affected by radial migration as all the other Milky Way stars. So we can study the structure where actually the star formed is an area that is starting now. We want to combine the integral field spectrograph that allow us to study the denser part of star cluster with the MOS to study the formation and dispersion of star cluster in a very different environment. At the moment, we are doing this study, but more or less locally, and then moving for a region like Arena, where you have several massive stars. It's a very different environment. And this will allow us to expand, if you want, the space of parameter. And then we want to study variability. So the idea is to, this is a beautiful plot that passed by Fateme and as you see, these are the different variability mechanism that has been observed empirically for young star. And you can see that there is a variability on very different time scale. The variability is associated both to the magnetospheric accretion, but also to the variability of the structure of the disk. And you have also extreme variability, like in the case of Orion, it's outer burst, but also small variability on very short scale. And the idea so that for part of the sample, or we have to discuss that, we will study, we will have observation at different cadence, and cadence of week and cadence of months, and also kinds of year, also decades, if we combine, for example, observation with WST with the observation that we are doing now with foremost and other instruments. And this to study variability on different scale. Also, just take into account that with the WST will probably use a CMOS detector, and so we may be able to study for bright star variability even in very small time scale. Is something that we have to consider and think about. Finally, this is a science case that we have to discuss, even with another working group, the working group that's working on resolve a population nearby galaxy. We want to study low metallicity environment, and this is to find low metallicity, we have to go either in the outer galaxy. For the WST is not very good because it's mostly in the northern sky, or go to the Magellanic Clouds. Since we need a big telescope, especially if you want to do to lower mass star. At the moment, we can observe only massive star in the Magellanic Cloud. And so we need to have a very large survey of young stars in the Magellanic Cloud. We need the WST. And this is and there we can study what do we study here at solar metallicity, essentially all this stuff from region slightly subsolar metallicity. We can study at lower metallicity. If someone in the last Lausanne meeting said that it's not low enough for the metallicity of the Magellanic Cloud, I understand that, but is at least a step forward, put in this way. So this is all. If you have question, comment, please let me know. And yeah, thank you
Great
very much.
talk. Thank you so much. So yeah, like 2 points. I think like first, like that other plot that you show, like this is not mine. So disclaimer, I just stole it from somewhere, like from the white paper, and then like installed it like everywhere because I thought like that is a phenomenal plot. So like it's like good to have it like on all of the science cases that are relevant. And secondly, I like to put a little bit Aloysa's work on the spotlight because I mean that is one of the like best papers that I read like maybe this year. And then Aloysa was also one of our speakers earlier this year, so please check out her talk, which is uploaded already on our YouTube channel. But yeah, like I mean this work that was about like the waves across Milky Way, this is phenomenal, got a huge press release, and it's very interesting. So if you missed it, like I really recommend you to go back to it and review it. Like that's phenomenal
Oh,
work.
I agree for this. And to be honest, so now we are preparing the second version of Science Case. From the scientific
Mhm.
point of view, I want to bit expand this part here. That probably was not enough. We didn't push enough because this is
Right.
probably the most newest part. Clearly, when we write the Science Case, we start from what to
I
put
know, yeah, right. But this
together.
is like
But
such
it's
fresh work, yeah. Like, and the idea behind it is just mind blowing. I know, like,
uh,
it really got me excited.
this idea to use young star to study this huge
Yeah,
structure,
right,
whole galaxy is very
right.
interesting, and we want to. I think it could be the main goal of this WST.
Yeah, sure. And then, like, how much it would evolve with LSST because you will also like do a lot of like astrometry with that, like for younger stars, especially like if you're on top of that working group as well. Like we're gonna know even more before WST is operational. So I'm very much like looking forward to like what comes like from that front as well. So yeah, Richard, please go ahead.
Thanks very much, Germano, for the very nice presentation. I was wondering, in terms of variability, would you be, with the MOS, would you rather focus on the low or the high resolution spectrograph? And what would be the typical resolution requirements there to see something interesting?
I think we want to focus on the low resolution because I think the main thing is go far away. And for studying the accretion feature, you don't need a very high resolution.
Mhm.
Probably if I would choose myself, I would choose something a bit slightly higher than what they're planning, more on 6,000 and 4,000. But I think with 4,000, you can really do a lot of studies. Now there are also the IE tools that allow us to squeeze a lot of information for low resolution spectrograph.
Mm-hmm.
So I think we're really the main instrument is it's the low resolution instrument. For what
Okay.
the high resolution, we will use that, and there's two advantages. One, that we may do chemistry. It's more complicated, very complicated, but I hope that in 30 years we manage to have a good abundance, very precise abundance of young star, and that one you need really the high resolution. And probably the high resolution would be important for very precise radial velocity. If you want to study dynamics, maybe when we need the radial velocity precision. But to study accretion and variability, I think the low resolution is the one.
Okay. I was asking this also because the definition of the windows for the high resolution spectrographs may want to consider which lines would maybe be particularly interesting to detect variability. Am I correct to assume that mostly you'd be interested in emission line variability, or is this also absorption line variability you're looking for?
The variability itself, the emission line, the superficial are photospheric and not supposed to be variable. So
Right.
yes, so the part that is more interesting is actually the UV part. I don't know if we'll arrive there as much, especially in the first version. But I think there is some emphasis because for measuring accretion, the best tool is the Balmer jump, the continuum emission.
Mm-hmm.
But that I don't think we will arrive with the WST. There are anyway the emission line that correlate very well with the mass accretion rate, and so you can use them for studying variability. From this point of view, the high resolution could be interesting to study the variability of the shape, for example, to do more the dynamical study. So I want to use both instruments. Probably with the low resolution, if you want to do measure mass accretion rate, if you manage to use lines and to arrive to some precision, it will be interesting. The high resolution, if you want to study more structure morphologies, then because you need to do dynamics, and then you need to do the profile sensitive of the line. But yeah, there are specific lines. And then, of course, we should be careful to the spectral windows. There is an ongoing work on the spectral windows, I think.
Yes, absolutely. George Kordopakis is the one leading this. And yeah. I also wanted to use the opportunity, since you mentioned clusters and variability. I'm not sure, this is now shameless self-advertising, I apologize. But earlier this year, Emily Hunt and we put out a paper where we searched for variable stars in open clusters within 2 kiloparsecs. And that sample contains more than 4,000 young stellar objects that are variability selected in 169 clusters. So it may be an interesting sample for you to look at in case there are some objects in there that you haven't seen yet. Just wanted to mention this, and I'll post a link to the paper in the chat in case you'd like to have a look.
No, that's amazing. Thank you.
Something that we should understand for how many stars we want to do this variability study, not for all the stars.
Right.
This
True.
kind of work is useful to understand. As observed, this will be important to do this simulation that I want to do. So
yeah, especially like in terms of like how many snapshots do we want, and then like for how long, etc. Like because like all variability is about that, right? And then like no one has like monitored these stars in a spectroscopic sense. So the data is like fresh, like no one has like basically focused on this type of science.
So in Gaia DR4, you will get spectral time series for all of the stars that are observed, right?
Yeah.
So with RBS, it would be limited to relatively bright objects, but in BP and RP, you'll get pretty much every star.
But then like that is like BPRP, right? So the resolving power doesn't help you at all in the concept of like accretion. Like you can see like some continuum variability, but then like no lines. So
But at this stage, what we need to prepare WST, it's to know how many variables you have, and so you
Yeah,
can
right.
hide
Which is good. Yeah,
for
right.
because I think the variability, especially the study on short time scale, we have to do on a
Right.
amount of time, not on all the sample. So this Gaia data and also this work done by Emily and Richard are fundamental because we say, okay, I will do for the 1% of the sample, I will observe like every week, I don't know.
Yeah, right. And there can be like, I don't know, like a candidate sample, and then like we add up to that, like, I mean, stage by stage, just say that, oh yeah, like, I mean, for example, like we studied this like golden catalog, for example, of the stars, and then like we just like expand this because we got like good results, or like, no, it just dies because like the results that we wanted like didn't come out of that.
And this is fundamental to this feasibility study because I mean,
Exactly. Yeah, right.
in cadence it's complicated, so you
Yeah,
cannot.
right. No, yeah, but then like very interesting to just understand like what is an optimal approach, the entire
And
program.
if I may just ask one more question. So in WST, one way that we're considering to collect time resolution is by splitting the observations for every target into multiples. And so we would get maybe 3, maybe 4 observations easily of every target. Is this already something that is useful for your science case from the point of view of variability? And what would you draw from that?
Allora, so yeah, okay, yeah, I have this plan that every target should be observed 2 or 3 times. Allora, this is in general useful for binary, like the start. So if you have twice 2 observations, give very useful observation of binarity. And it can be useful to properly estimate the radial velocity precision because you have repeated observation. And then you have the long-term variability that you can study very well, and maybe can open your discovery space because in young star, having a properly understood of long-term variability, even it could be interesting. Then when you go to short-term variability and or these erupting variables, then you don't need to do on the whole sample. You want to do I think to a subsample.
Yeah, so I think what we have planned so far would be to specify a minimum and a maximum duration between visits, so that presumably you would get 3 observations with different intervals in time between them, but they might be spaced over the course of a season or possibly longer, depending on how things are specified.
Having said that, I mean, having for an instrument like I've been in foremost, no, and putting strong constraint cadence may complicate things a lot. I mean, so I might guess from my experience at some point we will have to loosen up a bit the constraint, but let's start on what we aim and. In general, even have serendipitous repeat
Right.
beautiful, I think.
True. This
So
is very important, right? Because I mean, like you might catch a star in the accretion phase, or like I mean, for 5 years, the star might not be in accretion phase. So I mean, like whenever you're looking, it's something that you're really not aware of, like what phase the star is in. But then I think like 3 or 4 per year is like the standard, right? Like we don't need like more than
So
that.
it's
3, 4 per
so
year, it's a lot.
to
Yeah,
clarify,
three,
it's not
four is
3 or
like
4 per year, it's over the course of the survey.
Yeah, okay.
right. Okay.
And it might be taken within a season or it might be spaced longer, but that's the total number of observations for the survey
Yeah,
period.
that I think will be useful for some.
It's more something that allows you maybe to subsample or filter stars for further analysis and gives you a large statistical sample to work with.
Yeah,
Exactly.
exactly. Right. True.
Okay, thanks a lot again.
Okay. Any other questions, comments, even? Okay, so if not, I think we can close the session here. Thanks again, Germano. This was very interesting. I hope like people took something away from this. And I mean, I thoroughly enjoyed this. Thank you so much for being with us today. And yeah, looking forward to more collaboration and then like writing the white
We'll
paper.
keep in contact, and then at some point we will converge to a strategy together.
Of course. Yes.
Okay, bye bye.
Awesome. See you
Bye.
around.
Thank
Bye.
you.
Ciao.
Bye-bye.
Bye, thank you. Bye.